Hello, Wharton Warriors. This is part 3 of our interview questions. The topic today is machine learning. I'll tackle 2 tough questions, one from Morgan Stanley and about Gaussian distribution, and another from Uber on principal component analysis, PCA. So let's dive in. I've prepared 2 questions here. Please take a look at it and think about it on your own, and I'll solve step by step. Okay, so our first question comes from Morgan Stanley. Say we have n observation for some variable, which we model as being drawn for Gaussian distribution. So this is same as normal distribution. What are your best guesses for the parameters of the distribution? So to answer this, let's first recall that a Gaussian distribution is defined by 2 parameters, mean mu and standard deviation sigma squared. So the goal here is to estimate these parameters using maximum likelihood estimation, MLE. If you're unfamiliar with MLE, please refer to the previous video. So what was our likelihood estimation of normal distribution? So the likelihood function for observations, x1 through xn, is just probability of x conditioned on the certain mu and the standard deviation sigma squared, which is the product from I equal to 1 to n, 1 over square root of 2 pi sigma squared, an exponent of e minus xi minus mu squared over sigma. 2 over 2 sigma squared. Okay, so what is our likelihood function? And we take the logarithm of the log likelihood function. If you take the log of this is just, we get negative n over 2 log 2 pi square root sigma squared minus 1 over 2 sigma squared, sum from 1 to n, xi minus mu squared. So to find the MLE for mu, we take the derivative of the log likelihood with respect to mu and set it equal to 0, like we did last time. So the derivative of the log p of x conditioned on mu and sigma squared over with respect to mu is just the 1 over sigma squared, sum of 1 through n, xi minus mu, and we set it to equal to 0 because this part doesn't have mu. So this part just goes away, right? So this is a simple mean. Okay, so simply to find, also let's find the MLE for sigma squared. We take the derivative with respect to sigma squared and set it equal to 0. So we can do the same thing here. It's just this time it's just for sigma squared. So the x conditioned on mu and sigma squared over sigma squared, right? Conditioned on sigma squared. So what is this? This is a negative n over 2 sigma squared plus 1 over 2 sigma to the 4th power, sum 1 through n, xi minus mu squared equal to 0. Okay, so this is the sample variance, right? So in summary, MLE estimates for Gaussian distribution parameters like we did last time. So the MLE estimates for the Gaussian distribution parameters are mu hat 1 over n, sigma 1 through n, xi. This comes from MLE. Also, the estimate of the variance is 1 over sigma 1 from 1 to n, xi minus mu squared. So this also comes from MLE. Okay. All right. So now let's move on to the principal component analysis from Uber. Describe the idea behind principal component analysis and describe the formulation and derivation in matrix form. Okay, so PCA, principal component analysis, is a technique to reduce dimensionality of the data while retaining as much variance as possible. So the key idea is here to transform the data into new set of variables, the principal components that we say, which are uncorrelated and ordered so that the first retain the most variant present in original data. So if you code, you might see the data that comes like this. First, the first component has the highest variance, and then it goes down. And it's up to you how many variables that you will contain, right? Okay, so suppose we have a data set X with p variables. So the goal is to find a set of vectors So what is our goal? Goal is to set vectors, find a set of vectors, find the vectors W1 through Wn. It's up to you. I would say K here. K here first, where K is less than or equal to P, right? So you can set the number of principal components that you want to have. So the first principal component, Y1, this is our first component, is given by, we transform the first vector with and multiply with X. And the second component, Y2, would also be W2 transformed X. So how do we maximize our variance here? So the principal components are obtained by solving the optimization problem here. So the maximum of W, so we want to have as many W's as possible to get the highest variance, right? So the maximum of W of variance of this WT X is equal to WT sigma W, right? We sum every W's, right? And what is our constraint? We have to, all these has to be an orthogonal. So WTW, the dot product must be equal to 1. So here, the sigma here is just the covariance. This is the covariance of the matrix of the data, right? So how do we solve this problem? We use Lagrange multipliers. So Lagrange multipliers, how does this work? This works by performing an eigen decomposition of the covariance matrix of this. So we perform the eigen decomposition of this matrix. So if you perform the eigen decomposition on this matrix, what will be the eigenvectors? Our eigenvectors would be Wi and corresponding to our principal components that earlier we defined, and the eigenvalue gamma I. So indicate the amount of variance captured by each component. So the first principal component corresponds to eigenvector with the largest value or largest eigenvalue. So what is our first principal component? This corresponds to the largest eigenvalue. Normally in interview questions, they wouldn't ask you to calculate out of these, but you just have to know that our first principal component, the biggest principal component, and the most important principal component is the eigenvalue containing the largest eigenvalue. And second to the next largest, and so on. So the eigenvalues themselves represent the variance explained by each principal component. So in summary, PCA finds directions. So I will write it here. So PCA also finds the directions. This is the vector. Directions that maximize the variance in the data. So that maximize the variance of the data. Okay, so the largest components ordered by the amount of variance they explain. Okay, so this wraps up our deep dive into these challenging data science interview questions. I briefly went over it. And if you have any questions, please leave them in the comments and I'll see you in the next video. Thank you.